In chapter 13, where we are discussing trigonometry, we're going to be addressing triangles and how that they play in space. And you've learned a lot of that in geometry and isosceles triangles and right triangles, 30, 60, 90 triangles. We've learned that all triangles have to add up to 180 degrees. We've learned how triangles can sit out in space, but we are going to be transferring these triangles and understanding whether they're working so that we can then put them on a coordinate grid. Because in algebra, what we have often been doing is putting everything on a coordinate plane. And so then we have points that we are graphing. So say this is the point 4, 5. We are going to use what we know about our triangles to begin making some decisions about points that are in the coordinate plane. So that's where we're going. We're gonna start with a small part and then we're gonna keep layering it on to the next things. So the important thing for trigonometry is there's some terminology that we need to know. There are 6 terms, 6 trig figures, and they are sine. It is written with an E, but whenever we use it, its abbreviation is just SIN. There is cosine, and that's labeled COS, and there is tangent, TAN. They all have matching inverses, and that's not any different. We've learned that with matrices, with numbers, with all of our graphing of our equations. Everything has an inverse. So the inverses of them are cotangent, written COT, secant, written SEC, and cosecant, CSC. And if you notice that when we're looking at them in a chart form, our inverses are directly above each other. And so these are our pairs. And you can see that every single one has a base word and a co-word with it. That we don't have any that match up with cos. So you don't have like a cosine and a cosecant together. The easiest way to remember that is I go in a circle around, and we're always gonna say the word and then it's co-word. The word and then it's co-word. So we have sine, then cosine, tangent, then cotangent, secant, then cosecant. And when done in this order, it will keep your inverses lined up orderly. So those are our words. How do we actually play our words with our triangles? Well, one thing that's important to note is that when we are using sine, cosine, tangent, and their inverses, we are specifically talking about right triangles. So one of the things that we know is that every triangle has to be 180 degrees. If we have a right triangle, this takes up 90 degrees. That means that our 2 angles on the other 2 parts of our triangle must add up to be 90 degrees. So that's a shortcut that we can always use finding out what we have for our angles. Now, in math, we often talk about our unit values. That means when we have numbers of 1. Numbers of 1 are easy to work with because we don't technically have to write them in our formula. So we're gonna address 2 very specific right triangles and come up with some values that will be either memorized or put in a chart, things that you need to know. The first one is a 45, 45. Excuse me. One of the things that we need to address whenever we're talking about angles are made by 2 different rays. So if I have 2 different rays and I have, say, these markers, and I decided to make an angle between them, I would spread out the 2 different sides or the 2 different rays, and I'm going to measure this angle that goes between them. The angle between them determines the distance from the top parts. So if my angle is smaller, then my distance is smaller. If my angle is greater, then my distance is greater. So something that we can take away from that is that the side length opposite our angle, so the length that is made from the two rays that form that angle is directly proportional to the actual angle. So if it's a small angle, then your side is going to be small. If it's a large angle, then your side is going to be large. Given that, we can look at an isosceles triangle, which means two sides are exactly the same, and say we have a 45 and a 45. My angle is exactly the same. So if my angle is the same, and I'm setting this up here, then that means the distance from where they terminate has to be exactly the same. So for all 45 isosceles triangles, we can say that the two sides are exactly the same. I'm gonna put X. If we're looking at our unit 1, we would say, let's call these sides 1. So if they're each 1 in length, it leaves us a question: what is our hypotenuse? Now, a formula that you need to know is that called the Pythagorean theorem, and it states that for a right triangle, this only works for right triangles with a 90-degree angle, that for a right triangle, that one side squared, the side that is touching the right triangle, and the other side squared have to add up to equal your hypotenuse squared. Okay, so a squared plus b squared equals c squared is the way that that is written. And then we can solve for any of our variables if we don't know them. So in this case, for a 45, 90, we could say that 1 squared plus 1 squared has to equal c squared. It has to be this unknown over here. So I have 2 is equal to c squared. And according to our roots, we're going to take the square root of both sides. We have the square root of 2. Now, typically, we would say plus or minus the square root of 2, but a negative distance does not make sense when we are actually measuring something that is valid. Okay, so for all isosceles triangles, we can say that the hypotenuse is the square root of 2, or x times the square root of 2. So if I had a triangle and the sides were 2, and I had 2 and 2, then I would have 2 square roots of 2. There. The other triangle that's very important is a 30, 60, 90 triangle. So again, we have our 90 here. If we choose to make one side 30, the other has to be 60 because these have to add up to be 90 degrees. And now we have a smaller angle, so it's going to be a smaller side, and a larger angle, which is going to give us a longer side. There is a very special relationship between the shorter side and the hypotenuse. Again, the hypotenuse always has to be across from the 90-degree angle. So if our shorter side is x, our hypotenuse is always 2x. It is 2 times our shorter side. So if we are given a 30, 60, 90 triangle, and we say that our side is 4, we can automatically know that our hypotenuse is 8. There is always going to be a 1-to-2 ratio between these two values. So that leaves us to find out what is our extra side over here. Well, in this case, we can still use our Pythagorean theorem, and it says that one side, so x squared, plus our other side, I'm going to write b squared, is equal to 2x. The entire thing is squared. So according to exponents, we have to distribute. So I have 4x squared here. I want to solve for b squared, so I'm going to move x over, say minus x squared, and I get 3x squared equals b squared. We're going to take the square root of both sides. So now I simply have b. My square root of 3 has to stay, but I need 2 and I have 2 of the x's. So my x gets to escape. So I have x square root of 3. So if we have written this in our unit triangle and my x value is 1 and my hypotenuse is 2, that means my other side is the square root of 3 because I was choosing 1 for that. So in this one, if we know that b is x square root of 3, My x is 4, so my b value here is going to be 4 square roots of 3. 4 square roots of 3 for that side. So those are some special values that we know our side lengths will line up. So how do we then use these values that we know to fill in this information for sine, cosine, and tangent? Okay. So there is a mnemonic that we can use, and it's called SOHCAHTOA. And it is simply sine is your opposite side over your hypotenuse, cosine is your adjacent side over hypotenuse, and tangent is your opposite side over your adjacent side. Now, the angle that you are addressing determines which sides we're looking at. If I am looking at this top angle, then my opposite side is down here. However, if I'm looking at my bottom angle, my opposite side is over here. For a 45-45, that doesn't matter, but for a 30-60, it does. So for a 30-degree angle, my opposite is x. For the 60-degree angle, my opposite was this square root of 3. So we need to make sure that we are standing in the right place, that we are looking at the right sides. So when we are looking, there's a chart in your book that you can follow. These are values that you're going to need to memorize. Specifically, when we are addressing a 45-degree angle, put that through here. Our opposite is going to be 1. We're going to use our unit triangle. Our opposite over our hypotenuse is 1 over the square root of 2. Now the problem becomes that we can't leave it like that. We learn that we have to rationalize the denominator. So we're going to multiply by the number 1. We can multiply anything by the number 1 and it doesn't change it. I'm going to choose my number 1 to look like the square root of 2 over the square root of 2. So on the top, I now have square root of 2. On the bottom, I have square root of 4, which I know to be 2. So we're going to write for a 45-degree angle that the sine value is square root of 2 over 2. Now we could work out our adjacent over hypotenuse, but we've already said that they're exactly the same. So we're going to say that our adjacent is the square root of 2 over 2 as well. Then there's a special value for our tangent. Tangent addresses the ratio between both sides, and both sides are exactly the same. So our tangent value will always be the value of 1. Now, to find the other ones, our inverses, we're simply going to flip them over. If I flip 1 over, it's just 1. If I flip the cosine over, I now have 2 over the square root of 2, which means I have to rationalize it. And I'm going to end up with 2 square roots of 2 over 2, and these cancel. So we're simply looking at the square root of 2. And then we know our cosecant will then match as well. So these are the 6 values that you need to know for a 45-degree angle. The ones that we need to learn for a 30, 60, 90 triangle, address these. Okay, so if we are going to have our triangle, and we're going to use our unit triangle, and we're going to say I have a value of 1, and that is our smaller number. I've got 60 as my larger one. The relationship between these two is twice that. So I know I have 1 and 2, and by the Pythagorean theorem, we found out that the other side is square root of 3. Do you notice that it is 1, 2, 3? So that's a good trick that we can have. We can go 1, 2, 3 around. This one just happens to be a square root. So according to our SOHCAHTOA, our sine for 30 is going to be our opposite over our hypotenuse. So sine for 30 will always be 1/2 because we are addressing that ratio. Our cosine for 30 is going to be our adjacent side, so the side that's touching it, square root of 3 over 2. And our tangent is going to be our opposite over adjacent. So we're looking at 1 over the square root of 3. We cannot leave it like this. We're going to rationalize by multiplying by the number 1, and we end up with the square root of 3 over 3. Okay. To find our cosecant, our secant, and our cotangent, we're simply going to flip our numbers over. and get 2 over square roots of 3, which will rationalize to 2 square roots of 3 over 3. And then we have 3 over the square root of 3, which is going to rationalize to simply square root of 3. Okay? So for finding our 60, we're simply going to go the opposite direction. So here's a note. When I look at 60, my sine is opposite over hypotenuse. It matched the cosine of 30. So when we're addressing our 60 and our 30, our sine and our cosine are simply just going to be switched. Whereas the sine for 30 is 1/2, the cosine for 60 is going to be your 1/2. And where your cosine for 30 was square root of 3 over 2, your sine for 60 is going to be square root of 3 over 2. Because all we're doing is we're addressing the ones, it was an adjacent line here, adjacent side for the 30, but it is the opposite side for our 60. So these 3 angles set up in your table is what that you need to have memorized, and you need to know how to work through those problems for your homework. Okay, we talked in class about some very special values called Pythagorean triplets. So Pythagorean triplets are special values that fill out that Pythagorean theorem of a squared plus b squared equals c squared without you having to actually do the work. You can always do the work, but if we know that 3, 4, 5, so that side hypotenuse always works out to be this. We also had 5, 12, 13, and any multiples of these. So you can multiply all of them by 2, all of them by 3, all of them by 4. Same thing, we can work our way down, and those are special values that automatically fill in our side, and hypotenuse without having to do the work of the Pythagorean theorem. So why would we want to use this, and how do we put this into practice? Well, if we are given 2 sides, then we know how to find the other side. We've got the Pythagorean theorem for that. But if we are not given 2 sides, and we are only given 1 side and 1 angle, then we can use our trigonometric functions to find all 3 angles and all 3 sides. First, if we're given 1 angle and we know it's a right triangle, we can say it has to add up to 90, so I know that one has to be 30. Then I can also say I know that the sine or the tangent of 60, and there will be multiple ways that you can solve these. So you can, because all of these will work. They're all valid, and it's valid for all of your angles. We never use it for the 90 degrees. Okay, so there might be different ways that you get it. You might get it a different way than your friend, or a different way than even I wrote it. But I would say that the tangent is opposite over adjacent. So if I want to find x, I would say x over 3. And we'll use a calculator to plug in that number. So on your homework this week, when you are asked to find all the values of a triangle, we are looking for all 3 values of our angles and all 3 sides of the triangle. You will need to solve for all of that. And we're going to use our sine, our cosine, and our tangent to say, what do I know? Which one do I want to plug in? Because those are the values that I know. If I am given a side and a hypotenuse, I'm going to want to use one of my formulas that includes hypotenuse, and either with 30, the adjacent side, that would be the cosine, or the sine of 60. So you could solve it 2 different ways and get the exact same answer. If I am given 2 sides, I'm going to want to use tangent for that. If they ask you for a cosecant, secant, or cotangent, you can simply find the ones that you know and flip them over, or know that if I was going to look at CSC, it's hypotenuse over opposite, secant is hypotenuse over adjacent, and cotan is adjacent over opposite. So you can either flip it afterwards or you can flip it beforehand.